तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last two lectures, we have seen how to design sequential circuits and also to implement the design and also how to implement the design using MSI components like multiplexers, ROM, PAL, PLA etc. in for the combinational part. As you know that a sequential circuit will have a combinational part and a sequential part. Sequential part is usually the flip flops, registers, and the combinational part is can be implemented using any technique that we are familiar with. You can use gates. First lecture of the last two lectures, the first one we saw the methodology of implementation where we only used gates for the combinational part of the sequential circuit design. And the second lecture, in the last lecture, we saw that the combinational part can be replaced by MSI components, medium scale integrated components such as multiplexers, ROM, PLA etc. Now I want to take that design procedure a little further and show you how to fit in a design of a sequential circuit in its totality. Like for example, take a system. Earlier example we just took equations and implemented them. Now we will take a whole system and see how a system is implemented, because this is how in practice you will have to do. In practice they will give you a design, a system to be designed with input output specifications properly drawn, and you ask all questions to get complete picture, clear picture of what is expected of you, and then you go to the design procedure and then try to find a hardware to implement the design. So you know, when you do that, we will try to choose a hardware which can best fit in the design. You can best fit of the design, smallest or the simplest hardware that we use to fit in the design adequately. So it should have all the features that we want, but it should not be overkill for the problem. So from this point of view, I thought we will take one example, one final example of the PAL design, and that will be explained. That is why I call it a system design example. So this will be a vending machine. So the system we are going to design is a vending machine. We are all familiar with vending machines. You have these machines where you have this slot in which you put a coin and you get a service, a coffee, tea, or some candy bar, or a can of soft drink, whatever. This is a very common thing and can be very easily done. It looks like a complex device, but in practice it is not. In reality, a vending machine is a very simple concept. So that is what I thought I will, this gives you the concept of how to go about designing a practical system and also how to fit it into an existing hardware like a PIL. What are the features? To make this design simple again, a classroom lecture or a lecture always has to make it simple to avoid the getting into the complexity of the hardware. In order to drive home the concepts and the points, it is better to keep the system design simple. We are going to say this is what we are going to design, a vending machine. Which will dispense, let us say, about how many items? Let us say 5 items. 5 items will be dispensed. So, this is output. Each of these output will drive the. See, you know how these things are done. There will be a sort of a mechanical device which holds the item to be dispensed. Some sort of a relay has to operate and release the mechanical device so that one item will fall into a tray and pick it up from the tray. Supposing it is candy, 5 different types of candy bars will be kept in 5 different trays which are controlled by held in place by mechanical devices tightly, and just by operating a relay, you release one of the trays, and the tray one of these holders, and the content of the holder falls on a common tray and you pick it from the tray. That is how it is. So, it can be a candy bar, it can be some soft drinks, or it can be different types of merchandise like fruits and whatever. Now, to make it simple, as I said, I am going to call this 5 different items will dispense. Also, to make it simpler further, I am going to make it all equal cost, and also by a simple coin operation. We have a coin like a 5 rupee coin. You insert a 5 rupee coin into the slot, and if there is a proper coin of 5 rupee coin, it will release, it will be recognized as an input, and any coin other than 5 rupee will not be recognized, will be rejected, and there is no provision for giving change. Supposing you do not have a 5 rupee change, you put a 10 rupee note, it will not accept it. All this I am making these extra restrictions to make its design simple, so that we will concentrate on the design aspect. These features can be improved later on. Once you understand the concept behind the design of these things, you can always improve the features by incorporating all these additional things. So, in order not to lose track of the design concept, I am making it simple. So, I am going to say I am going to have a separate coin acceptor, I am going to call this. This is a unit which is independent of our machine. I am not even going to design this. I am going to assume that this is available. A coin accepting mechanism is available, which is a slot into which you insert the coin. You can make it a 5 rupee coin or a 2 rupee coin, depending on the type of what you want to sell. If it is a candy bar, probably you would like to have a 2 rupee, or if it is a soft drink, you may want to have 5 rupees, whatever, beverage. So, once the correct coin is inserted, there will be an optical mechanism which is not going to be part of this design. These things are available, you can buy it ready made. So, there will be an optical mechanism will compare you can set it for 2 rupees, 5 rupees or whatever, or if it is a multiple coin also it can do. You can make it one at a time. Suppose I want to put a change of 5 rupees, 2, 2, 1, it can keep count, all that. I am not going to discuss that part. So, I am going to assume that there is a coin accepting mechanism, when the coin can be inserted here, and then once the coin is ready, it will say coin accept. So, it will give a signal, I will call the signal coin accepted. That means only when the coin is accepted, the vending machine will have work. Otherwise, the coin will be, it will fall, there will be a tray here again, a small tray here. If the coin is a false coin which is not to be accepted, suppose it is not a correct coin, or if it is not a coin at all, you put a metallic object or something, a stone, some people do this mischief of putting a stone into this. Such cases it will fall into this tray and you can take it back. So, only if it is the right coin, it will go into a box here, this safety box. Inside it will get stored here like a collection box you will find in temples, something like that. It will go into that and keep it there, and then it will give the signal. If it is not a valid coin, it will come out here and it has to be removed, taken away, and that is the only signal is expected of this, and this design is independent of this machine. I am assuming this is available. You can buy this and integrate it, optical mechanism and all that type of thing. And of course, once the coin is accepted and then you have make a selection, only then the selection will come. So, when the selection is over, when the coin is accepted, when the coin is accepted and the selection is proceeding, that should be a signal back from the machine saying that it is cleared. So, I should have a clear signal when you will clear this, yeah, so that next coin is accepted. Until the clear is done, until the clear is signal, so it will not accept the next coin. Only when the clear signal comes, this coin accept signal will disappear and the machine is ready for the new coin. So, you can even have some sort of a clear can be linked with a ready lamp. So, this can be a ready lamp, this also can be outside, I can also have it here, the vending machine can have it, it can be outside this. Only when the ready lamp is on, the clear can control the ready lamp. Only when the ready lamp is on, it will also be ready here. So, it will also say, so coin accept, so ready. This ready will also be for the vending machine also. Vending machine will be ready along with the coin acceptor, both of them will be ready at a given time. So, I need a ready output here also. Ready. So, these are my 5 dispense goods. I will call this output select 1, output select 2, output select 3, output select 5. One of these selects I will have to make, and there will be selection mechanism, that means vending machine not only the acceptor coin accept signal, it also needs the signal of which of these 5 objects, which of these 5 merchandise I want. That will be given by a separate switch setting. For 5 objects I can code it into 3 bits. So, I can have an LED display here, or not a display, I can have a BCD switch, it is called. BCD switch is I can set the switch to the position I want. So, the switch will give me the combination of what is required. So, if it is 0 0 0 0 0 1, it is YS1, 0 1 0 it is YS2, 1 0 1 it is YS5. So, what I want will be given by this switch here. Supposing it is 4 I set here, it will become 1 0 0. This is high, this is low. So, this is least significant, most significant. So, this will become 1 0 0 and this YS4 will be selected. That is how it is. Of course, you need a clock for this. And a reset signal. Well, the whole thing is starting, nothing should be on. So, all of them should be off, and then once you reset it, the ready will glow, and when the ready glows, this ready and this ready will be combined. These are the same signals. Actually, I am showing in two places. This ready and this ready, they both glow. This will accept a coin, and the machine will, and then what you do is, the procedure is, you set the switch first and then put the coin. When the coin is accepted, the coin accept signal will go, and then the corresponding thing will be dispensed, and the clear signal will come. The clear signal will keep the ready again, these two. Then it is time for setting one more selection and one more coin. This is the procedure for operation of this. And all reset can be done in different ways. You can have a reset by a switch button. You might have seen this by a simple switch. I am not going to talk about this in microprocessor circuitry. You know how to do a reset, power on reset. We can have a simple RC circuit which can do this job. With a normally this is high, this is VCC. When you short this, what will happen is, this capacitor gets charged the full value. When you close the switch, that switch capacitor voltage, the voltage of capacitor 5 volts is applied to this reset position and keep on for a while, and then that is the indication for the reset. So, this is a normal procedure they adopt in many circuitry for power on reset, they call it. So, this is how you push the button to get the reset signal. Clock has to be very slow, because it is a very slow process. There is no point in doing this very fast rate, because the signal has to be recognized and the vending machine has to dispense. There is no hurry about the whole thing. You can have a very low clock, but then the clock cannot be very low, because it is very difficult to extremely very low clock frequencies are very difficult to generate, because capacitance value becomes very large. You need a 555 timer. All of you are familiar with 555 timers. 555 timers requires a large capacitors for small low frequencies, and also with low frequency waveforms are generally not stable. Very difficult to have a very stable waveform low frequencies. Otherwise, there is no need for this frequency to be very high. So, you can have anything like a few hertz will do, something like a 2 hertz, 3 hertz. That's enough. So, the way it works is, as I said, the mechanism is wait for ready, lamp to glow, set BCD switch, to the required selection, insert the coin, there is only one possibility. So, correct coin I will say, insert the correct coin and collect the desired merchandise, whatever you call it, desired merchandise. Merchandise. So, the procedure is very simple. So, what we are doing is, the clock will go on. Let us say this is the clock. Zero one time. So, initial reset, when the reset is on, the reset it will take several clock cycles. Reset is a non-synchronous operation. It can happen any time because we are going to push the switch. When you reset it, we are going to push the switch, and then it is going to give the reset signal momentarily, and it can happen any time. And the next clock cycle, the ready will go at the next clock edge. This will be my ready signal. So we can have a ready signal as an active low signal. That is all right. This will be a ready signal, and this can happen only at this point. Even though my reset has gone low here, only at the next clock edge will my ready signal be available. I am going to call it ready low, does not matter. So, ready low will indicate the lamp. The lamp will glow whenever it is low, that is all right. We can have a LED connected to glow when the voltage is high, or you can have an LED connected when the voltage is low. You might have seen this in your earlier circuits, earlier course in digital design. We can make an LED on for 1 or off for 0 and off for 0, or you can make an LED on for 0 and off for 1 by connecting the anode and cathode proper polarities. We can always make it glow for 1 or 1 glow for 0. So, in this case we are choosing RDY to be low. When signal is low, the LED will go on. So, this lamp will glow. So, after this, the output, after this it takes some time because we already set the ready is there. That means we are going to select. You already, after this ready signal, only then you are going to set the selection and then insert the coin. So, it is going to take a while. I am not going to show those delays. So, after some time, the output will go, the selected output. So, let us say this is the delay required. After the ready, this is the delay required for the processing of the, and again this has to be synchronous. I am just saying in 1 clock cycle, does not matter. It can be 2 clock cycles, it can be 3 clock cycles. It can be part of a clock cycle, but then action can always happen in a synchronous logic. In a synchronous design, the action can always take place along the clock edge. So, the delay from the ready signal to the time the merchandise is dispensed will be depending on the circuitry. If it is less than a clock cycle period, the action will take place in next clock edge. If it is more than a clock period, let us say somewhere here it takes, then it will go here. So, I am just giving an estimate. We do not know the logic inside. So, I am assuming it is going to take 1 clock cycle. The next clock edge you are going to have the output generated here, and again for some reason we can also have is an active low or active high. So, we will have this signals active low. So, I will say this is merchandise. Since we have selected merchandise 4, OS 4 will go low at this point. OS 4 will go low at this point, meaning the availability of the merchandise. And then at the same time, clear signal will come and clear the, even if you are not taking the, there is no way you can find out whether you have taken the merchandise, the can of soft drink or the candy bar is in the tray now. What has been released from the mechanical holder, and it has already fallen into the tray. If you take it or leave it, the machine is ready to take next. So, if you do not take it, it is not your machine's fault. So, after the, you have to look for it. Once it falls, usually it makes a thud noise. Usually you might have seen those vending machines. Once this can falls in this tray, there is a noise, it is a sound. You know that it has fallen, so remove it. If you do not remove it, it does not matter because the machine does not know you have not removed it. There is no intelligence built into the machine. So, as soon as the machine is dispensed the can, it will clear the signal and next ready will go on, and then it is ready to accept the next input. This is the logic. Problem, actually we have given a problem statement so far, it has taken so long. That is the beauty, the design. You will have to be very clear about what you want. The conceptual design, the concept of the problem design, what are the various inputs and outputs, what is the interaction between them, what is the way in which you want the machine to work, and what are the signals and how they are going to interact. Everything has to be very clearly mentioned. Only then you are ready for the design. There are a couple of minor points I would like to make on the original specifications of the vending machine. Earlier I said that you set the number BCD corresponding to the selection that you want. Actually what happens is, since we have 3 bits S0, S1, S2, when all of them 0, the first selection is made when all the bits are 0, 0, 0, 0. That means really speaking BCD 0 should give the first selection, BCD 1 should be given the second selection, BCD 2 the third selection, 4 fifth selection, so forth. So actually what I am saying is, when you put a 4 here, it is 1 0 0, but since this is 0 1 2 3 4, this is not selected, OS4 is not selected, OS5 is selected. So for example, if you want to select OS1, you should put 0 here, and 0 will make 0 0 0, OS1 will select. This is only a minor matter. We could have done it the other way. We could have written this and then call these signals OS0, OS1. We could have written this here as it is and made combinations for 0 0 1, 0 1 0, 1 0 1, etc. That is all right. It is a question of convenience in the design. Second thing is about the reset. We said the reset can be done once the power is switched on. It is a power on reset actually. When the first time the power is switched on, there is this VCC and a capacitance, it is RC circuit. The capacitance gets charged, but then it takes a while. And this is a Schmitt trigger inverter. So there is a Schmitt trigger which inverting Schmitt trigger. So when the capacitor is low, when the capacitor is not charged to a particular value, the threshold value of the Schmitt trigger inverter, this will be low, it will be high. So that is the initial reset. The initial reset, as the power is on, the high reset input will be high, but once the capacitor has reached a particular value of the threshold of the inverting Schmitt trigger, this becomes low, high input, which means this will be low, so reset will be low, and that is where the normal functioning. So reset high is the period where it will not accept the signal from input or the coin ready, and once the reset is high, only then the ready signal will go on. That is why the ready signal has been shown as coming after the reset. After the reset is over, it is an asynchronous. The timing of this depends on the timing of the charging of the capacitor. RC time constant decides the time for which the reset is going to be high. Once the reset is low, it may not happen at the clock edge. After the next clock edge, the ready signal will go low, and that is the time when you can put the machine coin and then set the combination, then the coin. And the reason I told you this ready OS1, OS2, OS3, OS4, OS5, all these things are active low. There is no need for them to be low, but then there is a practical reason. When we later on show the implementation using the PIL, I will tell you why these signals are low. It can be low or high. These are the minor explanations I want to give on this before proceeding further. So having given the specification, having understood the timing sequence, we draw the state graph. That is the procedure. This is the state graph, a simple state graph. SR is the reset state, no output, and whenever the CI is 1, the coin accept is ready. Only with the coin accept is high, any activity will happen, because when the coin accept is low, it is going to wait. So if nobody puts a coin, the machine has no work. So, when the coin accept is low, the machine stays in the reset state, and if the coin has been accepted, somebody has put in a coin, the right combination of the coin, right coin, the right combination of coins, CA1, and then depending on the selection made, as I said, S2, S1, S0 is 0, the first choice. It is 1, 0, 0, 1, second choice, 0, 1, 0, third choice, 0, 1, 1 is the fourth choice, 1, 0, 0 is the fifth choice. So, the choice, based on the choice and CA being 1, it will go to the next state, the state being S1, S2, S3, S4, S5 for each of the combination of YS0, YS1, YS2, YS3, YS4. That is the reason we call these signals YS1, YS2, YS3, YS4, YS5. Even though according to the binary value here, BCD switch, 0, 1, 2, 3, 4 or the 4, 5 values, we called it 1, 2, 3, 4, 5 because here these are 5 states, state 1, state 2, state 3, state 4, state 5, state 0 being the reset state. Now, let us say we have the combination of CA and S is equal to S3 will be selected. To make the design simple, I can make an arbitrary assignment. There are only 5 states, 3 plus 2, 5 plus 1, 6 states. 6 states can be realized using 3 flip-flops. We can call these flip-flops ABC. We know how to do it. We have done earlier designs of combination sequential circuits using flip-flops, and number of states is decided by the number of states decides the number of flip-flops. But in this case, we make the design simpler. Also because we have the PIL which has more number of flip-flops available than we want, we have decided this assignment which is very simple. We will have one flip-flop active for each state. If all the flip-flops are 0, not active, then it is a reset state, and any one of these flip-flops active correspond to that state. So, let us say there are flip-flops 0, 1, oh I am sorry, S0 should be 1. So, there are how many flip-flops? 1, 2, 3, 4, 5, 6. There are 6 flip-flops. We will call these flip-flop variables A, B, C, D, E, F. So, I am going to use 6 flip-flops in this for 6 states. This technique is called one hot method. One hot assignment. The reason is one hot is one of the flip-flop is always active, hot is active. One of the flip-flops is hot, others are cold. Means one of the flip-flops is active, or other flip-flops are inactive. So, which the state decides the flip-flop, which depending on which flip-flop is active, you know the state it is in. If the flip-flop A is active, you know it is in state 0. Flip-flop B is active, you know it is 1. C is active, you know it is S2. D is active, you know it is S3. If E is active, you know it is in S4. If F is active, you know it is in S5. This assignment of assigning one flip-flop per stage as against the number of flip-flops decided with the number of states in the logarithmic fashion. For example, for 8 states you need 3 flip-flops, you have 8 combinations. This is a normal assignment procedure. This assignment procedure gives a simpler design, and if you have more flip-flops than you need in any system, you will use this method because the design is simpler. And in our case, we are choosing a PAL with a large number of states, a large number of flip-flops, and since we do not have enough number of states, we are going to assign one flip-flop per state. That is the one hot assignment procedure. So, that way I am going to make the flip-flop A active for S0 state, and output of that will be the S0 output. So, whichever flip-flop is active, that can be the corresponding output also. That is the advantage. If S1 is active, that means we are in state S1, which is YS1 state. That means output of flip-flop 1 B can be the output YS1. That is the advantage of this method. So, now we have to write the state table for this. You know how to write state table. I will do it simply, quickly. It is a long table because there are so many flip-flops. So, present state, S0, 1, 0, 0, 0, 0, 0. These are flip-flops A, B, C, D, E, F. Now we know that signals are CA, S2, S1, S0. These are the 4 signals into the vending machine. CA, reset is only once, after that this machine is working and clock is also not to be considered. These are the 4 inputs to the vending machine which decides the state transition. What is the present state, what is the input, that decides the next state. That input is decided by these 4 inputs, namely the coin accept and 3 signals correspond to the choice of the beverage or the merchandise. So, there can be, if it is 0, you remain in state S0, next state remain in S0 and output is coin accept. That means this signal will clear, and as long as these signals are coming, this signal is also called CCA. That means coin will be accepted, this is clear and keep it ready, but this is also 0. Now CCA is 0. I am sorry, output CCA. No signal will come. We are still in this state. Ready signal is already there. Now, you are in state S0, CA is 1, then there can be 5 combinations. So 0, 0 1 1 0 0 1 1 1 1 0 1 0 0, and then if it is a 1 0 1, this is not going to happen. We are going to be in state A, this is going to be in state B, state C, state D, state E and state F. Now, all others are 0 because one hot method I told you. There is no need for output separately written, because as I said the output is same as the flip flop state. So, if you are in this state, this also is output B. So, this is next state as well as output, and the other output to be given is when the transaction is completed. That will be given only when you are in one state and then you go to the next state. Now, what will happen to these inputs? The input is 101, 110, 111, which is not permitted, not used, not permitted, I will not say not used. There are 2 ways of doing it. You can make them as don't cares. If you make them as don't cares, what happens is the design will become flawed because some random number will come, and also possible there is a glitch occurring. If you design the state machine, sometimes these states may lead to some other one of these not used inputs can lead to a state which is a permitted state, and then it may dispense a merchandise which has not been selected. So, the other way to do it will be to use this also as fold it back. Supposing by mistake you put 5, you can make it the same availability as 1, something like that. So, you can say, for example, 5 can be made as S1. You can go back to S1, that means I can make it 1. This can be 2, 3. That means I am saying if I make a 5 combination, same output as 0 will come. 0, 1, 2, 3, 4, 5 will give you the same output as 0. If you make a 6 combination, it will give you same output as 1 combination. course. These 3 combinations can lead you to 3 accepted combinations. So, you can either put a board here, you can make a mention here for the beverage YS1 there is a tray, as I said, you can say select 1 for this, select 0 for this, you can say select 0 or 5 for this, select 1 or 6 for this, select 2 or 7 for this, 3, 4 you can leave. Otherwise automatically it can come. You make a choice of 5 or 6 which is not permitted, there are only 5 beverages, you put 0, 1, 2, 3, 4, 5, make a choice of 5 and put a coin, it will, without your knowledge it will come and you may not like it. There are 2 ways of doing it. You can say by default 5 will give this, 6 will give this, 7 will give this, that is without customer's knowledge. With the customer knowledge you want, you can put a label here saying that this will give, this can be gotten by either pressing 0 or 5, 1 or 6, 2 or 7, whichever is the way, whichever is the way. And then the next state S1, I am not going to complete this table, you can do it yourself. It is going to be when whatever happens it goes to the next state. Only when you go to the next state we are going to produce the signal. We are not going to produce the signal clear signal, CCA signal. The CCA signal will be cleared, the CCA signal will be generated which will clear the coin and then make it one more ready for accepting the next coin, and this ready maybe, these 2 may be tied together. Only when we go from the state after dispensing the beverage, it will go to the next state. So, this CCA will be one, that is only when S2, then S3, S4, S5. These are don't cares, I am sorry, these are don't cares. Now this machine you can now write from here to equations and then simplify it. Instead what we are going to do is to directly go to the PIL realization. You can write equations for A plus in terms of this A and this inputs, B in terms of this and inputs, C in terms of this and inputs, and etc., and for each of the outputs, as I said, outputs are same as the states as far as A, B, C, D, E, F are concerned. Only output which is outside this is CCA, and then of course ready is same as A. So the outputs will be ready is A, I need a space here. Outputs are state equation. I am skipping, you know how to do that. So write state equations A plus, B plus, C plus, D plus, E plus, F plus, and then the outputs will be ready signal is A. So if you are in a state S0, you will have a ready signal showing, and OS1 will be, the output 1 will be B, C will be YS2, D will be YS3, YS4 will be E, YS5 will be F, and clear will be when CCA will be any of these B or C or D or E or F. That is what it is, because CCA signal will be B or C or D or E or F. This one is 1, no? CA is, I think I made a mistake here in this table, this should be 0. Any of these signals will lead you to the next state. The design we have now completed can be fitted into a programmable array logic. The choice of the PIL is important. It needs registered outputs mainly, because there are all of these are registered output. There are states. We know that B, C, D, E, F, all of them are registers, states, and their outputs are also state outputs. So, we need registers, and also we need a combinational output, because of the clear signal etc. requires CCA requires a combinational output B plus C plus D plus E plus F. So, we need a device with registered outputs as well as combinational outputs and enough number of inputs. So, the one choice is 16 or 6. It is a 20 medium 20 series PIL which has 16 inputs, 6 registers. So, 16 inputs means it covers, there are 8 inputs here, you can see here 8 inputs, 9 inputs on this this side, on the left hand side. On the right hand side, the input number this 11, 12 etc. are bidirectional. See this is 12, input 12, 13, these are all 13, 14, this is 13, 14, 15, 16, 17, 18, these are 6 registers. So, we have how many? 8, 9 plus 6, 15, and then there is this IO, programmed IO, which is programmable IO, which is one here and one on the top. So, these are 2 inputs. So, totally it comes to 16, I do not know whether it comes to 16, yeah, 9 plus 6 plus 9 plus 6, 15, 6 registers, 9 inputs. Actually, the input number 1 is not counted as a clock. So, input 2 to 9 are 8 inputs, 6 registers, 14 and another 2 IO inputs. There are 6 registers as I already shown you. Let us see how to fit this into this design into this device. This is how we have realized the vending machine using this. The 6 outputs A, B, C, D, YS1, YS2, YS3, YS4, YS5 are the outputs of these flip flops. Now you know why these are negative signals, because there is a inverter. Each of these flip flop outputs there is an inverter, so that is why there is a negative outputs here. And then these, there are only 5 of them. The 6th register is used for ready signal. Ready signal, we know that we got this from the combination logic, which is in the state A. State A, B, C, D, E, F are the 5 states for dispensing merchandise, candies or candy bars or soft drinks. A is the reset state, you know that. So, corresponding to that we should have a ready signal. So, ready signal also comes out of this flip flop. So, A, B, C, D, E, F are the 6 registered outputs. Corresponding outputs are barred, RDY, YS1, YS2 etc. bar, and the inputs are of course, as you have seen earlier, we have shown reset input which is comes from that Schmidt trigger combination, the RC combination. The clock is given to the first pin, the S1, S2, S3, S2, S1, S3 inputs and no connections. The other connections are not used. NC means no connections, we are not connected. NC, these three are not connected. And CCA is, as I said, the combinational output of B, C, D, E, F. So B, C, D, E, F are also fed back. B, C, D, E, F are the flip-flop outputs, YS1, YS2, YS3, YS4, YS5. They are also fed back as inputs. So we can get this CCA output from this. Again there is a negative logic here, there is an inverter, the output of the OR gate, so it is CCA bar. And reset is given here because it resets all the flip-flops here. No, the reset is given here as the input to, there is a reset input here also. This reset input is here, that the tax is the same as this also is used for that purpose, right. This what is this reset? Yes. This reset is also used for the same, it is the same as that. And then the one final here, you have this G bar, which is not a term which is output or input, but G bar is an intermediate term. Since we did not write the individual equations for the A plus, B plus, C plus, etc., if you write them, there will be a combination which are common to all of these. That term we call G bar, and that we are realizing, and this combination is applicable to all the inputs. So G bar input is taken as the input to all the other registered outputs. So this is how we implement it. This is a design which gives you how to fit in the given specification, fully utilizing the capabilities. There are 6 registers, we have used all the 6 registers. We have used combinational outputs, we have used many of the combination inputs except a couple of them, and most of the gates have been used. So one of the optimum designs we can say. This is the way in which you specify, go through the design specification, write the state equation, and then implement it in PIL. Of course there are automatic software tools now available where you give the specifications, the tool itself selects the proper hardware and then fits it into the design. But I am doing it manually for you to understand the whole concept. With this conclude the design of the review of the combinational logic and sequence logic and design using MSIs and PLDs, etc. From next lecture we will be talking about implementing some of these things using Verilog hardware description language. Thank you very much.